So welcome everyone. Today we're going to talk about vibrations and their important influence in the world of homotopy groups. So usually, in comparison to homology, homology is easy. Homology is computable. We know how to work with it, but homotopy is kind of and we will see that for ourselves. So here I have an overview. The goal of this talk is to give you an overview of the main results that were covered, and hopefully that will be enough for you to discover more details and intricacies that we won't have the time to cover. So the two main results are, of course, related to vibrations. So we have a vibration called the Path-Loop Fibration. Just very briefly, omega of x is the loop space. So the space of all loops in x. Of course, you should include a base point for the loops, but I mean sometimes they are omitted. Okay, and then we have this isomorphism of groups. So you start with a fibration, and we will talk about what a fibration is a bit later. And you get this interesting result that is very general. So just to give you context, this second result, which is the Hopf fibration, let's look at it now. So you have pi n of S3, which is isomorphic to pi n of S2 for all n greater than or equal to 3. And that is quite interesting because normally S2 is just a sphere. And with the sphere, here you're fitting also spheres of higher dimensions. So maybe this is a small refresher. So pi n of S2 means fitting n spheres in S2. And I mean, naively speaking, loosely speaking, you would think that, okay, this is S2. You want to fit S3s inside of S2. Of course, it's going to be trivial. So the fundamental groups of S2 will be trivial. But and that's actually what they thought for most of the time in the 1900s. But then Hopf came, and he introduced the fibration, and he proved this highly non-trivial result. So that's already very good. And we can start by the Hopf fibration. So this is the theorem. And I claim that to get this result, we only need 3 other results. So they are, so to say, the ingredients to cook up this vibration. Not the vibration, I'm sorry, to cook up this isomorphism of homotopy groups. Of course, I presume you're all familiar with the concept of homotopy groups. And so that's why I don't spend much time on that. So the first ingredient we have here is that vibrations induce long exact sequences. Specifically, they induce long exact sequences of this sort. So if we have a vibration, and usually the notation for it is written like this. F could be thought of as the fiber, and B could be thought of as the base, and this is an inclusion map. So we can say that. So an inclusion map is when F is a subset of B. But yeah. So we have this vibration, and then in this exact same manner, it's like you just apply pi n from both sides. Of course, this is not what happens. This is not what happens, but similar to it. You apply, pi n of f, and then pi n of E, and then pi n of B, and so on. And this is the tool that we'll be using to prove this non-trivial statement about spheres, homotopy groups of spheres, specifically S3 and S2. And of course, this sequence is exact. We'll talk about that in a moment. And this is the first ingredient we will need for the setup. Then next, we will use this proposition, which I believe most of you might be familiar with. And it just computes the higher homotopy groups of S1. So as we've mentioned a bit earlier, S1 is just a circle. And the reason why we have Z, very loosely speaking, we're not going to have time to prove that, is because when you work with loops, you can count, you can set a positive direction and the negative direction. So let's say this direction is the clockwise direction. So one loop corresponds to +1, and then another loop could be in the other direction, the counterclockwise direction, then that's -1. And in reality, what we have is we have some sort of twisted, don't know the name for it, I forgot now, but you keep composing it like this, and you see how many loops you've created, and you can use some sort of floor function to see which integer is closest to the loop.
The word for that number
Spring.
is the winding number. Maybe that was the number you were looking for.
Yeah, the winding number. This is also a concept from complex analysis. So
Yeah.
the winding number can tell us how to compute Z. And for n greater or equal to 2, it is equal to 0. Mostly because there's only the identity involved. You can't really do much with S1, but we won't get into too much detail on that. And then we have a very simple lemma on exact sequences, but it's actually very powerful and key. So when I was preparing for this talk myself, I wasn't sure that such a simple result could be so influential. And I mean, if you want to prove this, well, you start with the isomorphism, and then so you go by the definition. So if this is an isomorphism induced by some map, let's call it F, and then what you have is that an isomorphism sends the identity to the identity. So if F is G1 to G2, then the identity in G1 is equal to the identity in G2. And you start from that, and you can actually prove this statement using the definition. But this is the trick, so to say. Maybe you could try it yourself. But simply, loosely speaking, also, just by the definition, so we have a function here, and a sequence is exact if the image of this function is equal to the kernel of this function. And so what is the kernel of this function? That's not so significant, but the image of F1 is G1, if I'm not mistaken. And from the rightmost side, if you look at the kernel of F3, well, the kernel is just everything that gets sent to 0, which is G2. And then the linking part is by looking at image of F2. Actually, yeah, so you look at image of F2, which is going to be equal to the kernel of F3. So I wasn't planning to do this, but I mean, I already got involved in it, so let me just finish it here. And what is the kernel of F3? This is G2. And if this sequence is exact, then the image of F2, and not the image of F2, but the kernel of F2 is equal to the image of F1, which is also no. Yeah, so I probably messed up something here, but that's okay.
Everything was perfect.
Really?
Yeah, 0 was correct.
Yeah.
So
But
image of F1 is 0, not G1.
No,
yeah, exactly. So the kernel, thank you. So I was just nervous, so I decided to just erase everything because I wasn't sure it was correct or not. So if the kernel is trivial and the image is the whole group, then you have a bijection between two groups, and a bijection between two groups is an isomorphism. So this is just roughly giving the details.
Yeah,
And
so what Omar is saying, let me just say it in rough terminology. If you have a long exact sequence and you can find places where you get zeros somehow or another by some argument, zeros below G1 and what he's calling G1 and 0 just above G2. The fact that that's long exact, the sequence is long exact, tells you that G1 is isomorphic to G2. It's a way to prove it's the main way, so to speak, to prove an isomorphism.
Yeah, exactly. And this exact sequence, so I like to call it the Augu lemma, because you have a 0 and 2 G's. So when I was referencing it in the LaTeX document, I'd write ref Augu. But anyway, so that's not important. Let's now prove the result. So we have our 3 ingredients, and as promised, here is the proof. But we first have to assume that this is a fibration by a function eta. This is something we have to define, and maybe I'll do it now. So
that's a good idea.
So eta is given by so these are complex numbers, and we look at twice of Z1 times the conjugate of Z2, and then you look at the modulus squared of Z1 squared minus Z2 squared. So this is the second coordinate. And you can check for yourself that the image of this map is a subset of S2. So it is a map into S2. You just have to square both components, and then you see what happens. And this map induces a fibration, and we will talk about that.
You're going to tell us what the definition of fibration is also, I hope.
Yeah, I will do this down below. So
okay, great.
Below here, but I just want to emphasize Yeah, but thank you for the question. So I want to emphasize the main result. I mean, this is of course key. The definition of the fibration is key, but I want to show first, while we're still focused, what we can do with the fibration, how a good definition can take you very far.
Yeah, very good. Fine.
Yeah. Well, the first theorem that we looked at and didn't prove yet, it says that you have an exact sequence that looks like this. I mean, there's of course a zero in the end and some technical part, but I won't talk about that for those of you who know. And so we have this exact sequence by the fibration if we assume that the theorem that I gave to you was correct. And then we use the fact that pi n of S1 is equal to 0 for n greater than or equal to 2. So we get this exactly. So this is 0 and this is 0. Yeah, do you see it? These are zeros and so on. And you get this pattern. Maybe I'll use a thicker line. So you get this pattern here. Which, guess what? It's the Ugu that I was talking about. So it's the isomorphism of groups, the lemma that we just proved. And from here, you can actually get that. So this is equivalent to the statement that pi n of S3 is isomorphic to pi n of S2. With some technical details, of course. So the n is equal to 3, you have to be careful.
You should always say for n in a certain range.
Yeah, for n. Yes, exactly. So I was literally just pointing that out. But thank you for the remark.
Well, maybe n greater than what about 2? Is 2 maybe still okay the way you've got this formula?
No, and we can actually show this. So if I
Oh, okay. So S3.
You want me to show it to you?
Yeah, let's
Okay,
see.
of course. So I'm just gonna make a new page here. Yeah. So just very briefly. So we had pi n of S1, and then it was the embedding into S3, and then it was the I'm ignoring the base points for now. I hope that's okay.
Yeah, that's okay.
Yeah, and then you get pi of n minus 1 of S1.
Exactly.
And of course, this is from the left and from the right. But and in the end here, we don't actually have so the sequence is exact in the sense that the kernel is equal to the image, but you might know that yes. So pi. So if we go on and write this until, let's say, pi 2 of S1, so that's the last 0 we will get, because for pi 2 is 0, but the other ones are not 0, so you get pi 1 of S3. No, you get pi 2 of S3. So you have to follow this, and then pi 2 of S2, and then pi 1 of S1 you need. So I think that's the key part. That's the key part. So pi 1 of S1, this is Z. This is not 0. So we cannot use our Ugu part, lemma. Because, so this is 0, but this is not necessarily 0. This is pi 1 of S1. And we've just, I mean, we haven't shown it, but we've provided that fact, which is it is isomorphic to the numbers, the integers. So this is why we can't have for pi 2, we can't have this setup where you have an isomorphism between pi 2 of S3 and pi 2 of S2. So does this answer your question?
Probably, yeah.
I
If
mean,
you would go on in that exact sequence that you've written there, where you underlined in red, the next term is pi1 of what would be the next term?
so you get pi1 of S3, then pi1 of S2, and then you get pi0 of S1, and from here you don't get groups. So pi0 is not a group. It's just the space of path connected components. You get pi0
Good
of S1.
remark.
Huh?
That is a good remark.
Yeah. So this is really important to highlight. But the sequence is exact in the sense that I cannot say isomorphisms. The function that takes that maps makes this map. It's called f. Then this map is exact such that the image of this map is equal to the kernel of the next map. Of course, you get pi0 of S3, and then you get a 0.
Okay.
In the end, there's always a 0. But I didn't want to include that because I wanted to just focus on the main.
I'm sorry, I diverted your attention. So
No, of course. I mean, I'm happy. I mean, I could spend the whole day talking about this, but I don't have all the time. Your time is very precious, and I want to make the most
okay,
of it.
good. So what do we know so far?
We've actually we actually know that if we can prepare those ingredients, we can actually cook up this isomorphism. So if we can prove this theorem, and this is something we will do in this presentation, and then we can actually do a lot of things. This we don't need to prove, and this we have already proven. It's the UGU part.
Okay.
With the lemma. But this will be the main. So if we go back here, so I have the big theorem. So I call it the big theorem because it's the theorem that you use to prove all the big results. And this is precisely the theorem that the fibrations induce the long exact sequence of homotopy groups. And now we can go on and talk about the second fibration. We will still go back to the main theorem, which is with regard to how the fibrations induce long exact sequences. But let's approach this result in a similar fashion to the first one. So we have this isomorphism. Lambda of x is the path space, so it's all continuous functions from the unit interval into x, such that it starts and ends at the same point. And in a case, so I've omitted the base points not to cause any confusion, but you could think of x naught as being your pointed space. So in this pointed space, you would choose the base point for the loops to be this x naught precisely. So it turns out that taking the loop space of x shifts the homotopy group. That's something we will prove, but we need also 3 ingredients, and this is well, this is the exact same slide that we had above. It's the same theorem, which we will also talk about. And this theorem has a corollary, which is the long exact sequence. So this is something, maybe some more insights to keep you hooked. So this is the fundamental group of a pair where E is a subset of F, and
The other way around.
yes, F is a subset of E. Thank you. E and based at X naught. So this is the generalization of the higher homotopy groups. If you take F, for instance, to be just X naught, then you get the normal higher homotopy group, something that looks like this. Say pi n E and some base point, it's going to be X naught. And there's going to be another base point, so we don't really need to write it down. But I think we can see now why it generalizes the concept, because this is a special case of the homotopy groups of pairs. So this is why it's a generalization of it. This is just some insight, nothing too much. And this is something we've seen a few minutes ago. And the second ingredient we will need is that the path space is contractible. So this is the path space. I'll write it not to cause any confusion. And it turns out that this space is actually contractible. And what does contractible mean? It just means that you can shrink it to a point. Intuitively, this should be obvious. I mean, if I have, and by chance I did not prepare this, but if I have some sort of path space like this one, you can think of all the paths on your space. You can actually shrink it to one point. So this is what a contraction is, and this is the idea of a contraction. Yeah, I totally just did that. This is the idea. If it's contractible, it's homotopy equivalent to a point. And this is the definition. I write a definition because you can actually prove these statements. I've proven them in the paper. So I can show you how you could do that. It's actually very simple. I mean, yeah. Let's not focus on that for now. But maybe just a small remark here. So pi n of px is 0. Well, this is not so obvious, maybe, but if you look at pi n, we have to, of course, identify the domain. So we have to say n greater than or equal to 1. So if you look at the fundamental groups of well, I'm not going to say 0, but let's say a point, x naught, then if you have a space, which is just a point, and you want to form a group out of that, then it has to be the trivial group. It's the simplest form of groups, which is just the identity element, because you just have a point, x naught, and that's it. So this is some sort of explanation. This is the only equivalence class that you could have. Maybe I'll actually explain this now. So if you look at all the paths that start at x naught, you can also shrink them to the same point because they're all in the same homotopy class. But that's another insight that's not so crucial for the talk. So let's move on to the final ingredient for this non-trivial result that we have. And this is something that we've seen. This is just the OGU. So I won't go over that. We've already done that. We've proven this lemma. And now we can apply the results. So of course, assuming that this is a fibration, and one can show that this is a fibration, you have this induced sequence, this induced exact sequence, and you use the fact that P of x is contractible, and then you use the fact that pi n of the path space is 0, and then you get the exact same setup. You get the OGU again. And so zeros on the right and zeros on the left, and two groups in the middle within an exact sequence. So it must follow that pi n plus 1 of x is isomorphic to pi n of the loop space. And this is a useful construction because we can compare spaces. So I can for example say that pi 5 of x is equal to pi 1 of just 4 gammas. Don't know the notation for that. Maybe just applying the loop space 4 times, for example. So it's some sort of way to induct on these spaces if you want to talk about loop spaces. Professor, do you want to say something?
No, that's very good. Continue on.
Yeah, okay. So we have this vibration, and then the exact sequence, and then this result, and then you have that. So the anisomorphism of groups, and this is true for n greater than or equal to 1. Because as we've mentioned a little bit earlier, pi 0 of anything is not a group. Is not a group. So that's why we have the result for n greater than or equal to 1.
Just a slight remark. In fact, that can also be interpreted for n equals 0 in this particular case, because
yes.
It's not, of course, it's not a group pi 0 of omega x, but if you take pi 1 of x, or am I saying something weird? Wait.
So pi 1, so this is why you want to write down, so pi 1 of x is equal
right,
to
so pi 1 of
0. Yeah.
Thanks. So I just want to say that pi 1 of x should be homotopy classes of loops.
Yes,
I think that's
exactly.
precisely the same as path-connected components of the loop space. Yeah, I mean that.
I mean, this is just a proof. I mean, literally just proof that, correct?
Yes.
So
Yes.
So it's probably an equivalent statement, but I'm not sure which part that we use first to prove the
Yeah, but
statement.
your remark incorrect. In this particular case, this is not an isomorphism of groups, but rather just an equality
of sets.
bijection of sets. Exactly. Okay, so sorry for please.
No, thank you. These are good remarks. And as long as we're learning something, that's always good. And finally, we can talk about fibrations. And with regard to fibrations, we have this thing called the lifting problem. So let's say we have a space like this one, and we have some sort of homotopy H like this one. One could ask the following question: if you have the homotopy and a map like F, and let's say that's some homotopy equivalent G, is it possible to lift up this homotopy to the other space? And the answer is, of course, this is not always the case, but for fibrations, this is by definition the defining property. And the defining property is the homotopy lifting property. And what it says basically is that if you have a map and you have a homotopy in the space B, and actually, so this is actually this could be a typo, or not really a typo. I mean, I could write this, for example, as the projection of the upper path. I mean, yeah. So the projection of this one is probably that one, and that's one way to think about it. And then we look at all maps and their homotopies. Okay. The homotopy of the projection of maps in here. And then we find a homotopy that's equivalent to it. So here I've not using the same letters. So we can find another homotopy, big F, on the space E, such that two conditions are satisfied. So F takes an argument, so argument for the function, and takes so you could say the time variable, which is in this unit interval. And at the start of the homotopy, you want to have this F in your statement, and then you look at, well, this is another thing you could look at. You project the homotopy that you just found, and you push it downwards. So you project it by the map P. And when you project it, you get the second homotopy, which is, in this case, it's going to be G. Now the drawing is just an illustration. And just to get the idea, so you have a homotopy in one space, and you want to look at the homotopies in the other space. And this is going to turn out to be the defining property for the fibration. I think I'm missing a slide. Yes. Okay. So I wanted the commutative diagram first. So I'll just pretend you didn't see that. So this is a commutative diagram. We have F as a map from X to E. Maybe I will do this. And then you have a map F that maps from X to E. So this could be your F. This is the inclusion map. And so it's given by, I believe, so I0 of X is equal to X and then 0. Yeah, this is what it is, but it's not significant. This is the homotopy that's given. This is the projection, which is usually we call the fibration sometimes. And then if we have this homotopy lifting property, and then we should have this homotopy between the homotopy that goes from X times the unit interval, as we've seen here, to E. And then when it goes to E, you project it. So you have, so is it clear? So you could get to G in two different ways. You can get to G by going just a straight path, which is how it's defined. But then you could also go up by the fibration F and then project it. Let me use another color. And then project it by P. And then you get the base. So this is good. And indeed, this is a definition of the fibration. Fibration is a surjection from a space E to a space B. Usually this is a subset of, so it's a subset of X, which satisfies the homotopy lifting property that we've seen. The most important part out of this is just to understand we have a homotopy in one space. You want to lift it upwards to the other space. That's all that it is. And then we need some other definition, which I'll just very briefly go over. So what we have here is a more generalized definition of the homotopy lifting. This is P. With the homotopy lifting property, just like we saw with the homotopy groups, the relative homotopy groups. Here, similarly, you could choose A equal to the empty set, and then you get, well, T is X times 0. So, and I'm right here right now. So if I put in T for this case, I get well, this is phi times 0 and 1 is just phi, and then I get X times 0. Yeah, I think I have a slight problem here. Okay, maybe let's not give this remark. But in general, one could show that if you take A to be the empty set, you just get the homotopy lifting property for a not a projection of fibration P and a space X. What is the purpose of this definition? So we can actually define these homotopies, but only up to homotopy of maps. So if you want to look, so if you go back here and you want to look at, let's say the function f here, which is projected, then it is too strict for you to ask that you commute this function as it is on the nose to the other space. That is way too terse for our purposes, and we only need homotopy in that case. So we look for a map that's perhaps homotopic to this one, and then we can work with it. So perhaps this definition will be more clear when we talk about the proof of the big theorem. And my apologies if it was not so clear, but it will be evident right now. So let's actually now read the statement of the theorem. And so we have P, which is a map from E to B. It is precisely a fibration. It is something that's called a Serre fibration, which is, it just says that, so just a technical remark. So if it's a Serre, I'm not sure how to say this name, fibration, then it satisfies the homotopy lifting property for all CW complexes. And if you look at our definition of a fibration, we use the Hurewicz fibration, which satisfies the homotopy lifting property for all spaces. And so actually, Serre implies Hurewicz, because it's not just spaces, but also you can consider CW complexes. So it's just a technical remark that's not so significant for our theorem here. So we have this setup. We choose a point B naught, and we choose an X naught such that the pre-image of B naught is X naught. So the situation looks something like this. So you have, this is E, this is B, map P, and then here's X naught, here's B naught. And we'll actually use this right now to prove the surjectivity. So what we will first do is we will construct some sort of initial lift. We'll construct an initial lift and then we will extend it by means of the relative homotopy lifting property. This is something that's written here, but it will become clear when we go over it right now. So let's precisely do that. So if you will give me a moment here. Yes, so how do we prove that it's surjective? Well, choose a map in the codomain. And then what does this map look like? Well, this is a map that looks like this. So it's a map, continuous map from I to the n to the base that we have here. This tuple just means that we map the n-dimensional interval. So I to the n is just 0, 1 times 0, 1, n times. This is a side note. And the boundary is just, it's given by this symbol here. And the boundary also has an explicit definition, but we won't need to use that. Just think of the boundary of a square, for example. And then we look at this mapping. So the n cube is mapped to, not precisely mapped to B, but it's a map from I to the n to B, and this boundary is mapped to the point. So the boundary is mapped to the point, which gives us an n sphere. So this gives us an n sphere. So pi n is space B, and you fit inside of it n spheres. And then what's next? And so we want to find the lift of F. So we want to find, let's say, tilde F, such that the projection of this function gives us our function back. And luckily, we might be able to do that. We might be able to do that if we use the base points. So we construct a map initially, just to see it, just to see it. We can look at the identity on X naught and see what it does. And so the identity on X naught, this is where it gets a bit technical. So j to the n minus 1 is the complement of the n-dimensional boundary, if I'm not mistaken. I could be mistaken here, so please ignore this. So it's a map from this is a subset of I to the n, and it maps into F. And here's the catch. Do you see it? All the arguments of this function will just get mapped to X naught. So we take the constant loop here or path, and then we map it using this assumption. So we get something that looks like this. So indeed, the projection of this identity at x naught is b naught, but this is not enough, because we still we don't need b naught. We need it to be function f, our function f. Remember, this is f, and this is f tilde. So how do we find this? This is the question. This is a good start, but how do we find this? So let me put this on the side, perhaps. Maybe I'll make a new page here just to make some space. Yeah, okay, that works. And then turns out that we can choose the following f prime. We can extend it because we have the fibration assumption. And I should probably wrap this up because I'm going over time here. So we use the homotopy lifting property to extend the following pair. And then we get a lift that is given by I to the n, I to the n, and then we map it immediately to our space, which is, well, just E. It's easy to get lost with all of those things. But of course, the boundary is mapped to this f that we have here. So f is just some subset in this region. The drawing is only good for purposes of imagination, but so don't take it too seriously. And then, well, if we have this is precisely the part where we conclude the surjectivity part. So it's a map from I to the n that maps into E, and boundary is mapped into F. So we can actually say that its equivalence class is going to be inside of the homotopy group that's given by the pair. I did not define what the homotopy group for a pair is, so maybe I'll do that in a moment. So P star of. So because we have a surjection, then this map between groups, it sends this homotopy class of the function tilde of f to just homotopy class of f, which is in by n of b. Let's just write by n of b. And I think there was a slight jump in logic here, but I will only say that it follows from this definition. Unfortunately, we don't have enough time to go over that, but we've at least proved that it is surjective. So we could say that this is half a proof. We can look at try to look at the positives always. You could also prove that it is injective. But we don't have time for that. And the key corollary, actually, so we don't have the big theorem. We actually have the big corollary we use this statement about the isomorphism of the exact sequence. So for the exact sequence, I have something that looks like this. Ends with a 0. So F and then E and then the homotopy pair. Maybe I'll define this group just for the sake of completeness. So base point X node is the set of all maps from I to the N. So it's sending I to the N. It's also sending the boundary of I to the N. It's also sending a subset. So J n minus 1 is a subset of I n minus 1. It's a face. It's a face in one of the n-dimensional cubes. So one of the faces. And now I remember what this J is. And then maybe I'll just write it here. This map maps into what maps into E. So I to the N is mapped into E, not precisely, but it's a function from there to there. F is mapped into the boundary, not precisely, but we want to have this inclusion. So we don't want anything from here being mapped to something outside of F. Sorry, that was a mistake. And then the face is sent to X node. And one way to think about this, because I know it's very technical at this point, is to think of the face for which you glue the two n cubes. That's a good analogy to think of. Now, if we want to prove this corollary, all we need to do is to use the isomorphism that we have, which is so we've proved that this is an isomorphism. And by the theorem, we haven't proved injectivity, but we proved that this is isomorphic to pi n of the base with, let's say, some base point b naught, but we can omit that for now at least. And the claim follows immediately when you just plug in instead of E, F, you can just plug in pi n of B. Then you get F, E, B as promised. Questions?
Well, it was very, in some sense, complicated. But let's just think of, for a minute, what you really introduced. You introduced somehow, the first thing you introduced was the notion of a fibration. You didn't spend too much time on it, but you spent some time on it. It means you have the homotopy lifting property. That is already a modern history. I think Serre introduced this thing not so long ago. But in particular, a covering.
Yeah, exactly. Yeah, 1953.
To me, that's not very long ago.
Yeah.
And you should keep in mind a perfect example of that is a covering space. Just
yeah, exactly. So if you take a continuum product,
space, and so the lift of a given lift would be looking like a spiral over a circle. So the lift might be a spiral. That's right. So
you can think of the projection. The trivial projection is this one.
Yeah, that's a good example, and a fiber bundle is another.
Yes, these are the fibers.
Yeah. So Serre really found a good axiom for these fibrations, And then somebody else, I don't know who, but introduced, in order to prove this theorem, introduce homotopy of a pair. So the
Yes.
pair EF. And it's very interesting. Don't forget, we already had the homology group of a pair. It looks rather formal at first, these pair constructions, but they're fundamentally important.
Yeah, and they're very natural as well. I mean, I was not so lucky. I had to go through lots of things in this presentation, so maybe I couldn't go too deeply into the concept. But maybe I'll say this one remark regarding fibers if someone wants to really understand them. So, for example, there's a if we think of a Möbius band. I don't know how to draw this. Dimitri, can you help me?
I don't think I can.
Okay. So I'll just state it.
Rectangle and identify two ends.
I'll just state, yeah. So I'll just state what I want to say. So a circle is not like a line. That's circle is very much like. I mean, just assume that this is the Möbius band, but this is trivial. This is the trivial bundle. This is non-trivial, and the idea behind this is just that if you go in close enough, I don't know how to draw. Maybe I can try. So I'm not sure. Okay, just yeah. So if you look at the
Möbius band is two-dimensional. Yes, look at it as a rectangle and with opposite sides identified with a twist.
Yeah, exactly. If we look at the Möbius band, okay, let me actually use this again, just by chance. Locally, if we zoom in close enough, the fibers that make this, let's say, this circle. This is not a circle, but just imagine with me that it is. The fibers that make up this circle are small rectangles in the sense. So from the outside, from the exterior, there are small rectangles locally, or should I say circles perhaps? This is some sort of torus. But if you look at the Möbius band, which is twisted, this is not the same. But if you zoom in close enough, you also have this.
Hey, sorry, I actually managed to draw the Möbius band.
Oh, that's amazing. Thank you so much. Okay.
Do you see it?
Try to. So thank you so much. I'm so happy right now because I was suffering. Sure. So this is, one could think that these two shapes are different from each other. So I'm just trying to draw like a normal band that's not Möbius, just a normal band. And this is a Möbius one. So the difference between them is this twist. But if we zoom in close enough, and I don't know how to zoom because if I zoom, this shape is still the same. But if we consider a local.
Now you're started. That's good.
Yeah. I'm glad you can see it because it's really frustrating not to be able to do that. So they are constituent of the same. Maybe I'll change the color. Same parts. So if you zoom in close enough, they have the same parts, but the difference is right here you have this shape, but you start twisting it, so it starts and then it goes back, and of course they have the same fiber, but no, is this correct to say? No, I wouldn't say that. But I mean, if you look at the small parts that constitute this this Möbius band, you get same small parts from the exterior that make up this normal band. So that's one key difference. This is the trivial example, of course, like this one or that one, but this is a bit non-trivial. I was hoping to show you this today, but I couldn't. I mean, I already did. I'm happy I can do that. I've also included that in the paper. So I actually have two examples. The first example is on trivial bundle, and the second example is on the Möbius strip. So if you want to check it out, just let me know.
So what happens with the long exact homotopy sequence in the Möbius band? Will that go into your paper or what?
No, just an example of of fibrations. For example, so you look at the map, which makes up this.
So there are two fiber bundles over the base. One is the trivial bundle, and another fiber bundle is
non-trivial,
right?
Yeah. I don't have the same bundle, but locally it's
locally it's the same.
Yeah.
Globally it's not the same. And does the long exact so in your paper you should really show how that example, the long exact homotopy sequence, shows that these two bundles are really not the same.
Yes.
Because you can compute, I hope you can compute, you can see the non-trivial bundle has the long exact sequence becomes interesting.
Yeah, exactly. It's just it wasn't so helpful to have these many topics, but I hope I really was able to just deliver the idea across.
Yeah, you did.
We learned something today.
It's very interesting. You need the loop space. You need various isomorphisms.
Yeah, exactly.
You need a good definition of a fibration. It's typical French. Serre found the right definition. Maybe in the context of Bourbaki, I'm not sure, because the geometers were looking at fiber bundles all the time, and Serre just pointed out you really don't need very much at all. You need the homotopy lifting property. That's it, and that's a nice remark of Serre. But the main examples are fiber bundles, are covering spaces, and so on.
Yeah, you could also construct it using manifolds.
Yeah. I'm very happy to handle the case of manifolds.
Not for me, not so much. I'm still a beginner.
Okay.
Yeah. Thank
Are
you
there
for your
other
attention.
remarks or questions? Dima, do you have a remark?
No, any other questions from someone else? If that's not the case, I think let's thank the speaker.
Yay!
Thank you, Omar.
Thank you for your attention.